Hello friends, in this video we are going to discuss about the bipolar transistor, that is the bipolar junction transistors basics. And these bipolar junction transistors generally is denoted as BJT, and BJT means bipolar junction transistor. Each part of this device, that is the bipolar junction transistor, has a meaning related to the structure and the principle of operation. The first word, that is the bipolar, signifies that the transport of charges, that is the transport of charge carriers, are both due to electrons and holes. That's why the name bipolar. Similarly, if we look for the junction terminology, so the junction signifies that the device contains two PN junction, that is two PN junctions connected back to back. That's why there is a name junction in the BJT. Similarly, we look for the transistor. Transistor means transfer of resistance, and from this the name came the transistor. So we can also call it as transfer of resistor. So if we take the word tran from here and resistor from here, so it will go for transistor. What does this mean, that the transfer of resistor? Transfer of resistor means an input signal is transferred from a low resistance area high resistance area. That's why it's called transfer of resistor. So this is the significance of the nomenclature of the device BJT. Now let us see what is the simple block diagram of a BJT. Normally a BJT are of two types. First one is the NPN, bipolar junction transistor, and second one is the PNP, bipolar junction transistor. So in the NPN BJT, it consists of three regions. First region, here there is the second region and the third region. So the first region will be of N type, second one is P type, and the third one is again N type. Generally, this N, first N is called the emitter, second one is the base, and then collector. So we can say this is the collector terminal, this is the base terminal, and this is the emitter terminal. So this is a simple block diagram of a NPN transistor. Similarly, we can draw a simple block diagram of a PNP transistor, and the PNP transistor block diagram looks like this. So it is a P type. Next there will be a N type region. Next another P type. So we can also name here that it is the emitter region, it is the base region, it is the collector. So there will be three terminals. The emitter, this is the collector, and this is the base. So we can write that the E denotes the emitter terminal, B denotes the base terminal, and C denotes the collector terminal. So there are three terminals in the BJT. That's why it is called a three terminal device. Now, what is the significance of this emitter? What will be the significance of the base, and what will be the significance of the collector? So let us see the significance of the each terminals. So first we will take the emitter. So in this emitter we can write that it is a region, it is a region to the left end which supply free charge carriers. That is, for NPN transistor, the emitter will supply electron, and for PNP transistors, the emitter will supply the holes particle. And these are the majority carriers of the emitter region. We can see that, and these majority carriers are injected into the middle region, that is the base region. So let us see the base terminal. So in the base, it is the middle region of the BJT transistor. For PNP transistor, for PNP, you can see the base region is of PN type, and for NPN transistor, the base region will be of P type. The majority carriers from the emitter region are injected into this region, and this region is very thin, in thinnest region we can say. So let us go for the collector. It is the region to the right end where charge charge carriers are collected. The area of this region is the largest. Compared to emitter and the base, the doping level of this region is intermediate. Now let us see how these regions are formed inside the semiconductor. So let us see what will be the actual structure or the device structure of the BJT. So next topic is the device structure. For device, so in the device structure, device looks like this, that there will be, looks like I'm drawing the total device in this way. At the bottom of the device there will be a P plus structure. Next there will be a region like this. There will be another region which will like this. So from this structure we can say this is the P region, this is the N plus region, and this is the P plus plus region. Now if we give a oxide layer at this terminal, so this is a silicon dioxide layer. Similarly, there will be a silicon dioxide layer here also. There will be silicon dioxide layer here, and there will be silicon dioxide layer here. So above this silicon dioxide layer, there will be a metal connection here. This is the metal connection required for making the terminals. Similarly, there is a metal connection required for this terminal, and there is also a metal connection required for this terminal. So you can see there is a terminal connected here, and there is also a terminal connected here, and there is also a terminal connected here, and also there will be a metal connection here also. So this terminal is the emitter region, and these two terminals will be connected together to form the base region, and this is the collector terminal. So this is the original structure of a PNP device. So this is the original structure of a PNP transistor, where the P region, that is the emitter region, you can see it is highly doped. Next, the doping, the base region is N plus, then it is the collector P. So from this structure we can see that the doping of the emitter region is the highest, and then the base region doping, and then the collector region doping, and this P plus region in the lower, it is the substrate is transistor. It is near about 100 micrometer thick. Originally the transistor is in the upper region, P plus, N plus. Now if we draw the doping concentration profile with the depth of the device, so in this axis I am putting the doping concentration, and this is the distance or depth, that is micrometer. Next, let us see the doping concentration here, and the doping concentration looks like that in the emitter region it is near about 0 to 2 micrometer, base will be 2 to 3 micrometer, and it is 3 to 10 micrometer. So here in the emitter region the doping concentration is the highest, and then comes the base region. In the base region the doping concentration is just below the emitter region, and the collector region will have a doping concentration lowest. And in the P plus region, in this P plus region it is of the doping concentration near to the emitter. So let us take some values. In the emitter, the doping concentration is of the order of 10 to the power 20 per centimeter cube, and in the base region, the doping concentration is the order of 10 to the power 8 per centimeter cube, and in the collector region, the doping concentration is the order of 10 to the power 16 per centimeter cube, and here at the P plus doping concentration is of the order of near about 10 to the power 20 per centimeter cube. So this is the doping concentration profile, and this structure is the realistic cross structure of the bipolar junction transistor. That means we can say that this structure is a realistic cross-sectional view of a bipolar junction transistor. Now for analysis purpose, a simple structure of BJT is needed, for which a simple equation can be derived and the essential phenomena can be clearly brought out. So for that case, we will consider the this cross section. So if we consider this cross section like this, in this way, let us consider the cross section, this dotted region. So if we draw the dotted region, then the dotted region will look like this. The dotted region will look like this. I am drawing here. So this is the P plus plus region. This is the N plus region. This is the P region. This is the P plus region. And here there will be a metal contact. So this is the metal contact. So there is a terminal emitter. There is a terminal collector, and we should have an extra terminal here to denote the base terminal. So this is the base terminal. Now for analysis purpose, to make the simple structure of the BJT, we will neglect this region. So if we neglect this region, then our structure will look like this. First there will be a metal contact, then the emitter region, then the base region, then the collector region, and here it will be a metal contact. So on this metal contact there will be the emitter terminal, and on this metal contact there will be the collector terminal. So this region is P plus plus, this is N plus, and this is P, and on the N plus region there is a metal contact. So this is the base region. So this is the original structure or this is the semantic structure, simplified semantic structure of the BJT, which will be used for the further discussions on the BJT, where we can find the simple equations and the essential phenomena of the BJT. In this BJT structure, if we draw this structure in a horizontal view, so we can see the horizontal view will look like this. This will be the emitter region, this is the base region, and here it is the emitter, this is the collector, and this is the base. So if I consider the PNP transistors, so it will be P plus plus, this is N plus, and this is P. So this is the emitter, this is the collector, and this is the base. So in this case, we can see that there are two PN junctions. So one junction is here, another junction is here. Here it is the first junction, J1, that is PN junction, and the J2 junction we can say it is NP junction. That's why this junction, that is the J1 junction, is nearer to the emitter region. That's why the J1 junction is termed as the emitter junction. Similarly, the J2 junction is also termed as the collector junction. So these are the two PN junctions here. Now, between these two junctions, these junctions are called the metallurgical junction. So we can say these two junctions are called as metallurgical junction. And the distance between these two metallurgical junctions is called the metallurgical width of the base, that is the base width. So WB is denoted as metallurgical base width. So this is the structure of the BJT, and this is the basics of BJT. And in this basics of BJT, we have found that the width of the collector region will be the greatest. Next, the width of the emitter region, and then the width of the base region. So according to the width of the three regions, we can write this equation. Similarly, if the doping concentration of this emitter region is in E, and if the doping concentration of the base region is in B, and if the doping concentration of the collector region is in C, then we can write that the doping concentration of the emitter region will be very much greater than the collector doping concentration, and the base region doping concentration is greater than NC, that is the collector doping concentration. So this is all about the basic design structure or basics of bipolar junction transistor. Thank you.